Huh? Ow. What is that? Yeah, this is the real deal in AP Calculus now. We can find the area between curves. I know. This, on the exam, very likely actually, that at least on the free response section, you'll have a question like this, where you will have two different functions here, and they want you to find that area that is bounded between both of them, all the way through the entire section of A going to E. Oh man, this is indeed one of the hardest sections, I would say, for someone taking the AP exam, but it is definitely something that we can go over and make sure that we are going easily through without any problem. So let's have a look here, because all of our work doing definite integrals in the last series is going to come up here and see how we're going to manage to solve this kind of problem. Okay, so going over the main ideas here is that with any sort of definite integral, it would only take the area. For example, if we looked at f of x, the actual definite integral would only go from the moment that it goes from the curve only down to the x-axis itself. Again, when we think about this, that's what happens if we took the definite integral, right, going from a to c of just f of x dx. Something like that would only take us from, like we said, the top of that curve down to only the x-axis, while it completely disregards anything to do with g of x. So, as a little bit of a key here, something that we need to remember going forward through these types of problems is that we will then take the integral. Now, the idea here is going to be fairly simple, but very profound for what we're doing here. We will say it's the integral of top minus bottom. Okay, so in that sense, we will go for that first function that is going to be on top and subtracted by the function that's going to be on the bottom. For example, in this small section right here for g of x, we have this whole section that we do not wish to calculate. As you can see, right, all this area that's underneath here, that needs to be taken away because that is not part of that area that is bounded between the two functions. And so that's why in this case, only from going up to c, because as you can see, that g of x now flips over to the top side between the two functions, is that if we were to write out just the section going from a to c for this type of integral, then we will take our first function f of x and subtract it by g of x and take it respect to x in terms of that integral. Pretty straightforward, because again, we're looking for the parts that g needs to be taken away from here, but also because the fact that g has some negative areas, some parts that are underneath the axis, well, that subtraction sign does make it so that this normally would have been negative area underneath a standard integral, but because of that negative coefficient, it makes all this into a positive area for ourselves. That's pretty good. And so that only goes from the function points from a to c, but then again, of course, we still have all of this to worry about going from c all the way to e. So if you want to continue with what the problem is asking for, to find the rest of that area right there, we need to add another integral, this time the limits then continuing from c to e, but then now, of course, is that g of x is now the top function and f of x is now the bottom function in terms of that function part here on the graph. So with that, we have g of x subtracted by f of x dx. Okay, now this is how you set up this kind of function right here. Again, keeping in mind, of course, is that our negative areas that are shown right there, again, because it's a minus f of x, this would now be increased to a positive value. And so all of this will be calculated forth as a total area for this part of that problem. Not so bad, but still definitely something that a lot of students will need practice on in order for us to really understand what they're asking for in terms of these areas. So why don't we go ahead and get to an example problem, and see if we can get something on this, like right. That's an example.
Oh yes!
Indeed it is. We have here the question asking us to find the area between two different curves. Y is equal to 2 over x, and this guy x plus y is equal to 3. Now, a graph would be helpful for us just to visualize what is happening here. And first off, this guy is not exactly in a nice graphable form for us, so we can change this to a y equals function of negative x plus 3. Now that is easily workable, as this is a nice negative slope straight line for us. So we can go ahead and graph this guy first, just so that we can get a visual on what is happening here. And so with 2 easy points here, we just simply connect those two. And that is going to be our first function. That's the y is equal to negative x plus 3, the easier one to graph. But now let's take a look at y is equal to 2 over x. Again, the whole point is that we need to know where those two functions intersect so that we can actually know our limits to this type of integral that we are going to construct. So to begin with, the 2 over x, well, we can run first an x of being equal to 1. That makes y is equal to 2. And hey, that does intersect there. And then with x being equal to 2, y is then equal to 1. And hey, that intersects there too. But of course, this is not a straight line. This is going to be the inverse function, meaning that if we go even further, like x is equal to 4, that makes it 1/2 underneath the 1 tick mark. And then with x being equal to 1/2, that would make y increase all the way up to 4. So we have something like this, and we can then see how this curve will look like going through something like this.
There you go!
We have ourselves a nice little part right there, that area that's shaded in, that is bounded between both curves. But now, of course, if we want to mark the points, is that at 1, 2 there's an intersection, and then at 2, 1 there is another intersection. So in terms of if we're only going from the actual vertical positions here, right, from how far they are from the x-axis, again, we will then go for our limits from a to b between those two tick marks on that function. So why don't we go ahead and construct ourselves a nice integral here. For this type of problem, remember, it will always be top minus bottom for the sense of what we are doing on this problem. So with that, our top function now being the actual linear function, the y is equal to negative x plus 3. So this is going to be our first function, but now that will be subtracted by our second function, which is the 2 over x. And of course, we are taking this in terms of x because dx means that, again, just like the Riemann sums that we have been doing in the previous series, is that we are measuring the vertical distance between the function and the x-axis and the area in between. So to round this all off, we then need our limits of integration going then from 1 to 2 like this. And there you have it. We have ourselves a lovely definite integral, which should be fairly easy to solve. So let's go ahead and see how this definite integral will pan out for us. So going through the integration, this will give us a negative 1/2 x squared plus 3x minus 2 times the natural log of x in there. Okay, and then we will evaluate this from 1 to 2. This should have been pretty simple for us, this line of work, of course, because we are so studious in terms of our integration that no one should get any of this incorrect. Now, let's go ahead and start solving in terms of the limits for this definite integral, and we should get to our final answer here. So, to keep everything together, we have a negative 1/2 times the 2 squared plus 3 multiplied by 2 minus 2 times the natural log of 2. Okay, and then with that, we then have the next segment here, which is going to be subtracted. Now this time plugging in the ones, which will give us negative 1/2 multiplied by 1 squared plus 3 multiplied by 1 minus 2 times the natural log of 1. So first off, this is a pretty easy simplification. The natural log of 1, of course, going straight to 0. And then with some final notes here is that we have the 2 squared making a 4, so it gives us -2 on top of this guy, and then a 6 from there, and then from this guy, and 1 squared times -1/2 is 1/2, and then a 3 after that. Okay, so we can then just put that all together into our next line of work back here. So we will then get a -2 plus a 6, and then -2 times the natural log of 2, subtracted by all of the -1/2 plus a 3. Okay, so now we just need some fractional help here, and we should be just about good here. So we get a +4 minus 2 times the natural log of 2, and then we finish off with a 3 adding a -1/2, which gives us 5/2, but it's still being subtracted, so we keep that in mind. Okay, and then lastly, with 4 minus 5/2, the last two combinable terms here, that will give us 3/2 minus a 2 times the natural log of 2. Okay, and that right there will be the complete area that is bound between both curves, again in that shaded region that we have right there. And that's because we are utilizing how we understand that we can subtract the different areas from a top minus bottom perspective, and therefore we get something like that. Okay, I think that's pretty good for what we have right now. So with this, we have actually a few other topics to go over in this new series in areas between curves, as we can now start getting into some lovely three-dimensional spaces with new equations that, like always, the AP test will not give you, and so will be something that you would need to memorize or be able to deduce based off of the problem. Sounds exciting, I know. So we'll be back here tomorrow with another section of different areas that we're looking to find. And from there, we should be another step closer to understanding how to answer those types of problems. Thank you all for watching, and we'll see you again next time.